right, break time is over. We're gonna examine our class. For break, we were talking about the special registers. We talked about stack pointer and base pointer. We have seen that the stack pointer and the base pointer are called special registers because they are there for a special purpose. Mainly, the stack pointer are used to access data in the stack segment, and specifically the stack pointer is used as an offset from the current stack segment during the execution of the instruction that involve the stack segment. For stack pointer content, it has to automatically update it, that is incremented or decremented due to the execution of a pop or a push instruction. Now, the base pointer, on the other hand, contains the offset as well in the current stack segment, which is used by the instruction which applied the addressing base addressing mode. Now here we have example. Before the push instruction, we have the content of the accumulator register, which is OX. Before push segment, before push instruction, we have before push instruction, we have our accumulator register content, which is OX 1000, and we have this is our stack segment, and we have our accumulator register, which is ABC stack segment, and we have the stack pointer, which is OX 0100. We assume that our accumulator register its content is OX A, B, C, D. Then after the push instruction, we have the stack segment is content, and we see that the stack pointer content has been updated by decrementing 2 because of the push instruction. Now we have the stack segment content. We have the SP content, which has been updated by decrementing 2 because of the push instruction. Now we can find out the value of our accumulator register, which is stored at a specific memory location, which needs to be found by adding by shifting 4 bits on the left to the left of the stack segment plus the offset. The offset in our case is the stack pointer, which has been updated because of the push instruction. With a push instruction, our SP needs to be updated by decrementing 2, but with a pop instruction, our SP needs to be updated by incrementing. This this clear to everybody? We need here to decrement Hello? Now, is this clear to everybody? Why our stack pointer has been updated? Because of the push instruction, our stack pointer needs to be updated. It needs to be decremented by because of we increment stack pointer. Okay? Hello? Questions? Is it clear? Now, I repeat myself. Stack pointer and base pointer are special registers because they are in our 8086 microprocessor for a special purpose to mainly access data in stack segment. So, stack pointer needs to be automatically updated after the pop or the push instruction. When the microprocessor is executing the push instruction, our stack pointer needs to be updated by decrementing the content of the stack pointer by 2. That is -2, okay? When we are executing the pop instruction, our stack pointer also needs to be updated. But in this case, we need to increment it by 2. So we need to find the memory location after the push or pop instruction. We need to add the content of the stack pointer after it has been updated. Now, we are going to talk about the source index and destination index, which are being used in what we call index addressing mode. These instructions are very important when the microprocessor is dealing with the data string. So we need the source index, destination index registers together with the data register as well as the stack, the extra segment, data segment and extra segment respectively, in order to differentiate the source and the destination addresses. These are also special registers because they help the microprocessor to make a difference between the source and the destination address. Now, it is very important to talk about flags because these flag registers, they hold various conditions after the execution of a specific instruction. Now, we have the CF. This is a carry flag register, which is set when there is a carry out or most significant bit in the case of addition or follow in the case of subtraction. So we have these carry flags that need to be updated depending on the result or depending on the carry or follow when it comes to addition or subtraction operations. We have the parity flag, which is set to 1 if the lower byte of the result contain even number of ones or for odd number of ones, it is set to 0. Parity. Even parity or the parity. What about this, right? Now, suppose you have the lower byte, which is this much, this data. The lower byte means 80 bits. You have 110011. That is 600. Now we have this lower byte. Our parity flag will be set to PF will be 1 because the total number of ones is 4. This is even, right? So this will be PF will be 1. For example, if the lower byte, the number of the number of ones in lower byte is odd, our PF will be set to 0. Clear? We need to count the number of ones in lower byte. If we have even number, our parity flag will be 1. If we have odd number, our parity flag will be 0. Next, we have auxiliary carry flag. This is set if there is a carry from the lowest number. Or we have 3 bits during addition or below during the subtraction. This is also important flag that we need when we are doing the addition or subtraction. We have the 0 flag. This flag is set also if the result of the computation or the comparison is 0. If you have the result of the computation or the result of the comparison is 0, you have this 0 flag which is set. We have the sign flag. The sign flag is also important when you are dealing with negative numbers. Negative numbers. We have this carry flag that needs to be set. The next flag is stop flag. This is the flag which is set when the processor is at a single step execution. We're going to see this in more detail when we start with graphic coding. The next one is interrupt flag. This flag is important because our 8086 microprocessor to recognize external mask interrupts. We have talked about the interrupts, but we're going to learn in more details about the interrupts. Interrupts are very important when there is a specific device which needs attention from the microprocessor. The next is direction flag, DF, to indicate the direction of the data, especially when you are dealing with string operations. We need this DF flag. The last one, overflow flag. The overflow flag is set when we have overflow. Overflow, maybe if you are working with the signed numbers, we need to have this overflow flag. Now, we have the 8086 microprocessors architecture summary. We have the general purpose register, pointers, index registers, segment registers, instruction pointer, and the flag. So this gives you a quick view about the 8086 microprocessor architecture. We have different flags. We have the name of the registers. We have their main function. This will help you to remember always about the main functions of the different registers that we have learned. It is very important because when we start lab, you need to know which register is important to which operation. Now we are going to start about addressing mode. Addressing method. We know that every instruction of a program needs to operate on data. So we need to learn about addressing mode, which are different ways in which a source operates the node. have this number 12 addressing modes, which are grouped in 5 categories. We have addressing mode for registers and immediate data. We have addressing mode for memory data. We have addressing for input-output port, relative addressing mode, improvise addressing mode. Now let's get started with register addressing. We have to move data from one specific register to another register. Addressing mode. Hello. For register addressing, the instruction will have to specify the name of the register which hold the data to be operated by the instructions. We have, for example, move CL DL. This means that the content of 8-bit register DL, that is the lower byte of data register, is going to be moved to an 8-bit register, which is the counter lower byte. This we call it opcode, and these are operands. This is the source operand, and this is the destination. Most of the time, the destination and the source operand need to be the same size. Another register addressing mode example is to move, for example, CX DX. This means that an 8-bit, 16-bit register content is going to be moved in a 16-bit register. Hello? But is this correct? Hello? Is this correct? Hello? Is this correct? Huh? Is this correct? Is this correct? Why is it not correct? Why? The source operand is register. Destination is also register. But tell me, is it correct or not correct? Huh? Is it correct? Is not correct. Why? We have the destination operand, which is 8-bit, but the source is 16-bit. So can you move 16-bit content in 8-bit register? Huh? Can you? Can you? No, can you? Can you? Can I use this? Can you put the content from this photo in this? No. Clear? So that's why this instruction is not correct. So the source operand and the destination need to be same size. Thank you. Okay? Alright, so this is not correct. Now the next one is addressing mode for registers and immediate data. This is not correct. we have immediate addressing mode, an 8-bit data or 16-bit data is specified as a part of the instruction. For immediate addressing mode, we have an 8-bit or a 16-bit data which needs to be moved to a specific register. We have, for example, the 8-bit data O8H given in this instruction, which is moved to DL. Or we have this 16-bit data, which is going to be moved into AX register. That is accumulator register. We have talked about the memory segmentation, that for segmented register, which are 16 bits, we needed to shift 4 bits on the left. Then we add the offset value to get the physical address. So this is to summarize what we have seen about the memory segmentation. We have segmented registers, which are 16 bits. We needed to shift 4 bits on the left so that we get the physical address, the base address, which is 20 bits. Then we add what we call the offset. And we have seen different offset for different segments. Now we have group number 2 of the addressing, which one we have going to see. The next is register indirect addressing. We have the name of registers which hold the effective address will have to be specified in the instruction. So registers are used to hold the effective address, and we see that we needed to use the following registers to found the effective address. We need the base register, base pointer, destination index, as well as the source index. The content of data segment register is going to be used as to calculate the base address. Here we have a simple example. We have to move the content that are specified by the location of memory location of the base register. They have to be moved in the counter register. So what does this mean? We first need to calculate the effective address, and the EF is given by the content of E effective address is given by the content of BX, and the base address, BA address, is given by the content in data segment, shift 4 bits to the left, and we have the physical memory address, which is given by the base address, BA, plus the effective address. In other words, we have the base address, which is given by the content in data segment, shift 4 bits on the left, plus the effective address. The effective address is given by the content in base register. Then we have got the physical address. When we need the base segment is needed to found the base address. The data segment is needed to found the base address, so that it's quite easy to find a 20-bit address given the BX as well as the base pointer. So this means that the content that are specified by this physical memory address is going to be moved to the counter register. addressing, we have the base register and the base pointer, which are going to be used to hold the value of the effective address. And a signed 8-bit or unsigned 16-bit displacement is needed to be specified by the instruction. In the case of 8-bit displacement, it is n sign extended to a 16-bit before adding the base value. So when we hold the value of the base value of the effective address, 20-bit memory address, physical address will be calculated from the base address or the data segment. So when we have the base pointer, to hold the base value, we also need to calculate the effective address by taking the base pointer as well as the start segment. Here we have the example, but in this case you see we have the content which is specified, the memory location of the base register with a displacement of a no sign 8-bit data. So we need first to have a sign extended of this 8-bit data. We have then to calculate the effective address, which is given by the content in base register plus the sign extended of the 8-bit data. Then we found the base address as well by taking the content in the data segment and shift 4 bits to the left. Then the physical address will be given by the base address plus the content of the effective address. Then we found the physical address. Then the content at this physical memory address will be moved to the accumulator register. Now we have index addressing mode. There we have the source index and the destination index registers, which are being used to hold the index value for memory data. And a signed 8-bit or unsigned 8-bit data will be used to be specified by the instruction. Displacement also needs to be added to the index value in source index or destination register to obtain effective address. In the case of 8-bit displacement, we also need extended to a 16-bit before adding the base value. Here we have an example. The procedure is the same. We have string addressing mode, which is being employed in string operation to operate on string data. String addressing mode needs to be used in string operation. We have most bytes. This is the syntax of string addressing mode, and we also need to calculate the effective address by taking the source index, base address, data segment 64 bits to the left. Then we calculate the physical memory. Direct input-output port addressing or indirect input-output addressing. We have these addressing modes that are needed to access data from a standard input-output map devices or ports. Here we have different examples. For example, in AL, the content of 09H that needs to be moved to the AL register. Then we have relative addressing. This mode of addressing, we need also to found the effective address. The instruction needs to be specified and needs to be relative to the instruction pointer. We have, for example, the zero flag. If this condition is not satisfied, the next instruction of the program will be executed. If it is satisfied, this needs to jump to the new address calculated by the default program. Implied addressing mode, this is the last one. Instruction used in this mode have no operand. There is no operand at all. So instruction itself with specify the data to be uploaded by the instruction. We have, for example, clear. This means that the carry flag will have to be set to 0 after the execution of this instruction. So this is what we call implied addressing mode. Questions? Hello? Questions about today's class? We talked about 8086 microprocessor addressing, and we talked about 8086 microprocessor architecture, BIU unit, and execution unit. We have found different functions of different registers in a specific unit. We have also tried to find the physical memory pointed by a specific segment. Any questions? No questions? We have a very small quiz for 10 minutes. Those who are sitting backside, as I said before, you may not get a paper. Only use this paper, okay? Those who are sitting backside, please move somewhere in front. Remember to write your student name and student ID. Student name, student ID, quiz number 4. Quiz number, everybody has got paper, right? Everybody has got paper? Has got paper. Only use this paper, okay? Please don't talk. If I found you talking, I will get back my paper. That means you'll be done. Okay? Tell me when you are done with question number 1 to 4. Finish? Finish question number 1 to 4, right? Finish question 1 to 4, right? Everybody has done question 1 to 4. Is this one? You have found the solution, right? I have found people who have not found the solution. questions about today's class? Okay. No questions? Okay, how many bits is address bus for 8086 microprocessor? How many? Address bus. There is address bus and data bus. That was one of the questions in the quiz. How many bit is address bus for 8086 microprocessor? Address bus is, data bus is 16. Address bus is 20. Okay? What is the memory size of 8086 microprocessor? Huh? 1 megabyte. Good. Okay? 1 megabyte. So you need to always pay attention to the teacher's instruction so that we'll be able to do well in your exam. Do not only sit mentally, physically present, but mentally absent. Okay? So we are done for today's class. I'll see you next time. But remember to finish your homework before Friday. Homework number 2 is due this Friday. Okay? See you next time.